if you recall from our previous discussions that if a transmission line is terminated into its characteristic impedance, so for example, if you have a transmission line, let's say a parallel two conductor wire, okay, which is your transmission line, which is propagating the electromagnetic energy. It could be a transverse electromagnetic TEM wave mode of propagation, and it's terminated into a load which is equal to its characteristic impedance. Then there is no reflection. Okay, so if, for example, at this interface, if this load is equal to the natural impedance or the characteristic impedance for a transmission line, and if you recall, if this transmission line is lossless, then Z naught is square root L over C, which is inductance and capacitances are distributed. Okay, so here we have the natural impedance as Z naught. So if that is the case, there is no reflection. So all the power is transmitted to the load. Okay. Otherwise, if ZL is not equal to Z naught, then in that case you have reflections. You have some of the power that is reflected back to the transmission line, and it follows that it forms a standing wave pattern. So as your VSWR, the voltage standing wave ratio, increases, it approaches to infinity, you are losing the power. Okay, I mean, if this is large, the ratio to maximum to minimum, maximas to minima of the standing voltage amplitudes, if that reaches to infinity, then you're not transmitting any power to the load. Okay, so you need to design an impedance matching network over here at the interface. So it is desirable to have ZL equal to Z naught in order to transfer or to transmit to have a maximum power transmission. If that is not the case, if ZL is not equal to Z naught, okay, then we have modified impedance of a transmission line which has, let's say, a finite length, call it small l, okay, and let's say for this transmission line which has a propagation constant k, which is in radians per meter, okay, how much it propagates per meter in radians. So for k, Z naught, these parameters, and small l, which is the length of the transmission line, we have a modified impedance Z prime. Okay, and that Z prime is not equal to Z naught if it is not terminated into its natural impedance, or if the transmission line is not infinitely long. Okay, so in both the cases, if it is not infinitely long and ZL is arbitrary, we have the reflections, so we have the standing wave ratio. Okay, we have a finite standing wave ratio, not infinity, but whatever it is, but it shows that there is reflection. So what we're going to do is we're going to find the input impedance of the line when it is terminated into an arbitrary load ZL, which is not equal to Z naught. Okay, now so if the transmission line, if you recall by the previous discussion, was terminated in Z naught, then it always present an input impedance of Z naught. So that's also equivalent to saying that if you're going to add another section of a transmission line of the same length, okay, so if here I add another length to the transmission line which is of the same length, I join these two, and which has the same characteristic impedance, well, the result is again the same, because you are looking at the impedance, that is Z naught. Okay, so even for example for this section, you have the characteristic impedance Z naught, propagation constant is K. So if you're going to join these two, somehow you still have the input impedance as Z naught. Okay, if either the transmission line is terminated into its characteristic impedance, or it is infinitely long. So adding another section does not results any reflections. Okay, so a piece of transmission line that is terminated with an arbitrary impedance Z, which is not equal to Z naught, is shown in this figure below. It will produce transformed impedance, that is Z prime. So we are interested in this Z prime, what this Z prime is for a arbitrary impedance. Okay, so for example over here you're looking into the transmission line. It could be a coaxial cable, it could be a two parallel wire conductor, it could be a hollow waveguide, whatever it is. Okay, but we are interested in the input impedance, given that ZL is different, or it's not equal to Z naught. Okay, the philosophy is that you see at this interface, and this is Z directed, your transmission line is redirected. So at in the interface where z equal to 0, since you know that at z equal to 0, you should have the constraint is that v of 0 divided by I of 0 should be equal to z naught. If that is not the case, well, this is not equal to z naught. This is some zl. Okay. Then there is some then there will be reflection. Okay, because this boundary condition should enforce z naught, but you have zl. So therefore, to satisfy this boundary condition, you will have some reflection. You will have a reflected wave back on the transmission line, and you won't have a complete transmission. Okay, so you will lose some power. And that's why the impedance matching networks are very common at both high frequencies and low frequencies. So, but again, at any point when you have a different impedance, the current or the voltage signal is sum of the currents and voltages, some of their, well, what it means is that you have a voltage that which is a voltage signal that is traveling down the transmission line in positive z direction, and then there is another say a reflected voltage, okay, and this gamma is a reflection coefficient, okay, which has a value of if you're going to take VR out, we have this VR over VF, which is the ratio of the reflected to the forward traveling wave amplitude. So basically, we're going to derive this expression for gamma, a nice expression for gamma in terms of the impedances. So if you consider the ratio of this reflected wave to positive wave amplitudes, this is gamma, and the idea is that you have both way opposite traveling waves on the transmission line, and then at any point z, it's the sum. Okay, at z equal to 0, you will have, for example, at v equal to 0. At v equal to 0, you will have the condition that is equal to 1 plus gamma. So that's your voltage amplitude. Okay, and this gamma is generally complex. So if the magnitude of the gamma is 0, which means there is no reflected wave, well then it's only the positive traveling wave, so there is no reflection. VR is 0. Okay, so that means there is no gamma. But in case where z naught is not equal to zl, you will have some reflection. Similarly, for you see I of 0 over here, this will be equal to you see v divided by z0 is your current wave. So this is 1 minus gamma. Why there is a minus sign? Okay, we are left with z naught over here. You see, if you recall in the previous discussion, since for the current, where is it? With regard to the current, it's positive when we're having a positive z-directed wave, and the current of the forward wave is IF forward VF over Z naught. But the current of the reverse wave, which is reflected due to an arbitrary load impedance different from Z naught, we have minus sign over here. Okay, so that's where the minus is coming from. Since the reverse wave is traveling in the negative Z direction. Okay, so that's how we are representing the reflected wave with the minus sign over here for the current waveform. So you see the division of these two, if you're going to divide this over here, if this does not come out to be equal to Z naught, well, you see, if the line was terminated, so if the line, if your ZL was equal to Z naught, then in that case, you see what has happened over here. If you're going to divide these two equations, okay, you'll have V by 0 over I by 0. You see, since there is no reflected component, you will have this nicely, that it comes out to be equal to Z naught, isn't that right? Because why? Because gamma is 0. But since gamma is not 0, this ratio is 1 plus gamma, which is the reflection coefficient, over 1 minus gamma, multiplied by Z0. Okay, so unless gamma is 0, uh, which produces unless gamma is 0, which means there is no reflection, all the power is transmitted to the load. You're not going to transfer the maximum power. Okay, so we are interested in finding what Z prime is if ZL is not equal to Z0. So that's the objective. Um, so in order to do this, you see this figure shows a line of length small l. Okay, so this is from 0 to small l. So it has a finite length. The length is finite. It's a small l, but that's the physical length. Okay, if you recall, we discussed previously. This physical length is different from the electrical length. The electrical length is scale. Okay, electrical length is scale, and that means if you recall, k is the wave number or the propagation constant. You can write this k as 2 pi by lambda, and if you recall, if your length of the line is integral multiple of the wavelength, so in case if it is a quarter wavelength, then this comes out to be 2 pi by lambda by 4, which is 90 degrees. Okay, so that means simply a quarter wavelength transmission line is going to impart or produce a 90-degree phase shift, okay, between input and output. So that's the electrical length. Electrical length means how much phase shift does the line imparts, okay, it gives. So that's electrical length. So that's the difference between electrical length and the physical length. So figure shows the length small l, that's the physical length, whose right hand end, this is the right hand end, which is at z equal to 0, you have the load ZL, and it's connected to the load impedance. This side z equal to 0 is connected to the load impedance ZL. So assuming that an AC source produces a constant incident wave traveling to the right, and that is VF forward E minus JKZ, which shows that the wave is traveling in the forward Z direction, and that ZL causes a constant reflected wave in the other side. You see there is a sign difference. So this is plus over here, and we have a minus over here. So of course these two waves are in opposite direction. So this direction is to the left. So this is negative Z directed, and that's positive Z directed. Okay, this is positive Z directed wave. So these are traveling in the opposite direction. The factor gamma, as I mentioned earlier, is the reflection coefficient, and that gamma is only 0. Gamma can only be 0 if you don't have any reflection. Okay, that means under the condition that ZL is Z0, gamma is 0, no reflection, maximum power transmission. So this is what we desire, but then this is not the case. So gamma is not equal to 0 otherwise, if ZL is not equal to Z0. So at any point Z, the voltage on the line is actually the superposition of the two waves traveling in the opposite directions. If the gamma is 0, there is no reflection, you can see, but if it is ZL, which is different from Z0, then you're going to add these two voltages traveling in the opposite direction, which are forming a standing wave. Okay, so the corresponding current is again VF by Z0. Then you have the same expression of the opposite traveling waves. The minus sign occurs because the current in the reflected waveform is in the negative Z direction. So this minus sign is due to the direction of the current waveform. Okay. So how do we find gamma? Is okay if you consider V at Z equal to 0. So we are considering the waveforms, voltage and current waveform at Z equal to 0. You see this is the voltage waveform at Z equal to 0. This will be equal to, so this, if I find this at Z equal to 0, as we have done previously, this is nothing but 1 plus gamma. Okay, this is 1 plus gamma, and that's what you have over here. This is 1 plus gamma. Then similarly at Z equal to 0, you will have 1 minus gamma divided by Z0. So this expression reduces to 1 minus gamma divided by Z0. Okay, and if you're going to take the ratio of these two voltage and current expressions, well, at this interface, it should have been equal to Z0 for no reflection, but then if ZL is different, this is the situation, and gamma is non-zero over here. So you can rearrange this equation. This implies that ZL over Z0 and then again is 1 plus gamma, 1 minus gamma, and if you make gamma the subject of this formulation, you can find the gamma as ZL minus Z naught or ZL plus Z naught are a very important relationship. This is at Z equal to 0. Okay, so the reflection coefficient, mind this, that this is again the function of Z. It's space related. Okay, so we are finding this reflection coefficient at the interface where by interface I mean the impedance of the medium changes. Over here there's Z naught at Z equal to 0. This transformed into ZL. The medium changes to the load impedance different from Z naught. So you have the reflection, and the reflection coefficient is in terms of the impedances, okay, that are being considered here. So you see in the case where ZL is equal to Z naught, gamma is 0, okay, but unless it is so, otherwise gamma is some arbitrary complex quantity, okay. I mean, it could be complex because ZL could be inductive reactance or capacitive reactance, not necessarily it could be a real resistance, okay. So gamma could be complex in general. So expression for the input line impedance which we are after can be found similarly. Similarly, this is at Z equal to minus L, and what we are going to do is we are going to evaluate the voltage and the ratio of current to find Z prime, which is the input impedance, looking here, okay, at the input of the line. So Z equal to minus L over I Z equal to minus L. Similarly, you're going to substitute for Z as minus L over here. This is minus L. This is again minus L. Okay, you can see this expression. Here you have this expression. So this is E minus JK minus L plus gamma E JK minus L. Similarly for IZ, you see there's a minus sign over here because we are considering the reverse direction of the wave traveling, current wave traveling. Divided by Z naught, okay, and if you're going to rearrange this and you substitute this for gamma equal to what we have derived before, ZL, the reflection coefficient, the definition of the reflection coefficient in terms of the impedances, the characteristic impedance and the load impedance, ZL minus Z naught, ZL plus Z naught, then we can arrive at the input impedance Z prime, okay. So this is ZL minus Z naught, and then you multiply the this whole term by the numerator and denominator by ZL plus Z naught, so you will have this over here. And if you're going to rearrange this in terms of Z prime, because this whole thing is in Z prime, this is Z prime. So if you're going to rearrange this, you can find that you can write the expression as such. You can combine these exponential into sine and cosine and make a tangent of KL, where KL is the electrical length of the transmission line. Okay. So again, if you look at this expression carefully, there are some important features which can be derived from this relationship. So first of all, if you see what we are saying time and again is that if Z naught is equal to ZL, you see if Z naught is, if these two quantities are equal, then that means the numerator and denominator becomes equal, right? And that means your Z prime, for if I write this as Z naught equal to ZL, Z naught is equal to ZL, in this case, that is Z prime is basically equal to Z naught, no reflection. Okay, this is easy to see because the numerator and denominator are going to cancel out, so there is no reflection. Okay, so you can derive this from the relationship. So this relationship is general for Z naught not equal to ZL. For Z not equal to ZL, you know that the input impedance at any point on the transmission line as a function of small z. You see this impedance is space related. Okay, it has the argument of in terms of the length of the electrical length of the transmission line. So at any point, okay, if this is the case, well then okay, then there is no reflection. So Z prime is Z naught. So there are some special cases associated with the input impedance of the transmission line. So if ZL equal to Z naught, Z prime is Z naught for any length of the line. If ZL is 0, okay, so what if this is a short circuit? What if this is ZL is equal to 0? So in that case, let us see what happens. If ZL is 0, well, this is gone. This is gone. You don't need to consider these terms, and you are left with for, let me write this as ZL equal to 0, short circuit. Of course, short circuit is also not equal to Z0, so there will be reflections. That means this is not equal to Z0, but instead it will be J Z0 square, Z0 square tangent of KL. Okay, and it looks like that the it's an inductive reactance. But should this be the case? Well, by the way, this is just not Z square, because you see Z0 is going to cancel from here, and because this is 0, these terms are 0. Okay, this is 0, this is 0, so I have a short circuit over here. So this Z0 is going to cancel with this Z0, so we have just one Z0. Okay, so anyways, what I'm trying to say is that does this looks like J omega L? Well, would you consider this to be inductive reactance? Well, the answer is partially yes and partially no. This line will behave as an inductor if KL is small. If KL is small, electrical length is small. If KL is small, then you see for small arguments of theta, tangent theta is theta. Isn't that right? What I'm saying is that tan KL is equal to KL if KL is small. Okay, if this is the case, KL is small, and then you can see, then you can express the propagation constant in terms of 2 pi by lambda, and if this is also this is per meters, and then this is meters, so this will be radians. Okay, so yes, then you can have this as a radian, a constant, and the line does behave as an inductive reactance. It has inductive reactance, it behaves like an inductor, but in general the answer is no. Okay, so you see that Z0 is indeed J Z0 tangent KL, a pure reactance which is inductive for KL less than pi by 2, because tangent is positive for the arguments which is less than pi by 2 radians. So it does not produce a negative sign. Negative sign means you're looking at something. Negative reactance is due to the capacitance. So in that case, if KL becomes greater than pi by 2 or KL grows, then it becomes capacitive, etc. Okay. So in general, that is not the case, unless you're looking for a very short piece of a transmission line. Yes, then for a short circuit, the transmission line behaves as an inductor. Okay. Similarly, if ZL is infinity, so if ZL is infinity over here, then what you can do is you can divide the numerator and denominator by ZL, and then this will be 1, this will be 1 over here. This terms are going to vanish. This term is going to vanish. So you will left with a cotangent of KL. Okay, so over J or minus JZ cotangent KL, which looks capacitive because there is J in the denominator, and this is again for KL less than pi by 2. So for a very short piece of a transmission line, yes, it does behave as a capacitor, but then generally it is not true. It can be inductive. Okay, it can be inductive. Depends on the argument, or depends on the electrical length of the line. If the electrical length is small, yes, it is capacitive. In general, no, it can be inductive. So an impedance is left unchanged by a line of arbitrary Z0 whose length is half wave. So if you have k is equal to pi over here, if you're going to substitute, if the argument becomes pi over here, well, this is 0, okay, and so z prime is basically equal to ZL. So z prime becomes equal to ZL. Okay, you can see that in this expression over here, if this is equal to pi, this is 0, tangent of pi is 0, tangent of pi is 0. So this term is basically gone, this is gone, this cancels with this. So z prime is basically equal to ZL. So that means if z prime, looking into the transmission line, is equal to ZL, well then what is this transmission line doing over here? It is not transforming the impedance. Okay, so it's just like you don't have this transmission line, you are directly connected to the load over here. Okay, so the impedance is unchanged. So an impedance is left unchanged by a line of arbitrary characteristic impedance Z0 whose length is half wave. Okay, so half wavelength line, or not that. So they're not going to change the impedance, or an integral multiple of half wave, even k pi. Okay, so that is the case when kl or kz is equal to integral multiple of pi, half wave. So a quarter wavelength line, you see it imparts or odd integral multiple of quarter wavelength, results in a pi by 2 phase shift. Okay, so odd multiple of quarter wavelength line inverts an impedance, and that is equal to z naught squared by zl. So if the characteristic impedance is real, the load is real, then the transform impedance is also real. Okay, so a short is transformed into an open, and an open into a short, an inductor is transformed into a capacitor, and vice versa. Okay, so that's what this expression is implying over here. So if you have a short circuit, it's open, ZL is 0, Z prime is open. If it is open, then it is short. Okay, so basically inductor is transformed into a capacitor, and then this is vice versa. Capacitor is transformed into an inductor. Okay. What we have considered so far is that we have a transmission line that is lossless. Okay, so a lossless transmission line which does not have any dielectric filling, or you're not considering the resistance, which is the finite resistivity of the metal wire conductors. This is equal to, this is in terms of the distributed inductive and capacitor per unit length quantities. So Z naught is square root of LC for a lossless transmission line. This case is for lossless transmission line. What if the transmission line is lossy? What if the transmission line is lossy? That means you are considering the resistance of the wires. That means you are considering the dielectric effect of the capacitors. You are considering the shunt capacitors. So if you have a lossy transmission line, a line that causes attenuation of the signal, then what you do is, in the terms E minus jkz, what you're looking at here, E minus jkz, you add another factor, E alpha z. Okay, alpha is an attenuation constant. So what you do is, E jkz spatial dependence, space dependence of the wave, is going to be replaced by E minus jkz multiplied by E minus alpha z, and this is E minus jk minus j alpha. So you see over here, previously we had this propagation constant, which was equal to 2 pi by lambda, or you showed that this was omega under LC, and this was real. Isn't that right? So let's go back. What we discussed before was that K is real propagation constant for a lossless. This was again a lossless line. Okay, again this is lossless. Propagation constant for a lossless line is like this. But the problem is, if you are going to replace E minus jkz by E minus jkz multiplied by E into alpha z, then this propagation constant becomes complex. This is real, but K minus j alpha, where alpha is some real attenuation constant, this whole term is complex. Okay, so for a lossless line, the first thing is that the propagation constant is complex. Okay, and then again, this is for the forward wave, case for the forward traveling wave in the plus z direction. For the negative z direction or the reverse wave, this is E plus jkz. So we have E plus jkz multiplied by E alpha z plus alpha z. We have plus over here due to the opposing directions. So again, you have a complex propagation constant for a lossy line, and alpha over here is an attenuation constant. Okay, it's real. So now in a distance of 1 over alpha, you see what happens to this factor, what happens to this factor, what happens to this factor is that if I replace z by 1 over alpha, then you see that the amplitude is going to fall by 1 by E. Okay, by 1 by E. So for example, in this case, for the forward case, we have replaced this with minus alpha into z, and z is your 1 over alpha. So your amplitude is E minus 1, okay, or 1 over E. So the amplitude is going to fall by 1 by exponential, and the power falls by 1 over exponential square. Okay, this is the square of the voltage. or the current. So note that the K for a lossless line is simply replaced by K minus J alpha, so the propagation constant becomes complex. That's the first thing to notice. The other thing is that if a transmission line attenuation is, since the transmission line attenuation is usually expressed in terms of dBs per meter, you can find alpha. And how do you find alpha is that for a line whose loss is capital AL, given in dB per meter, since the amplitude is falling by E minus alpha 1 for 1 meter, okay, if this is 1 meter, so remember E minus alpha Z for 1 meter, you have this Z, and this is 1, this is equal to 1, and that is equal to E minus alpha. So this is how your amplitude is going to fall in 1 meter. We can write minus AL as E minus alpha square, or if you're considering this to be 20 logarithm, you don't need to write 2 over here. So this is equal to minus 20 alpha log E, okay? And if this AL is known, then alpha is AL by 20 logarithm of E, and that gives you the attenuation constant, okay? So the reason for this attenuation constant is the finite resistivity. You have the resistivity of metal wires, so you have a finite resistance, finite resistivity of conductors, or finite resistivity of conductors, and you have the other thing is that you have the dielectric filling, okay? So you have a finite permittivity of dielectric medium, okay? So these two reasons, they constitute the loss in the transmission lines. If the transmission line is lossy, the propagation constant becomes complex. If the transmission line is lossless, then your characteristic impedance or the natural impedance is real, and that is square root of LC, and which also has a real propagation constant, okay, K, which is the wave number of which is 2 pi by lambda, okay, and as the propagation constant is, as this alpha increases, you see you have more attenuation per unit length, right? And this is expressed in dB per meters.